Hello, my name is Jeff Morgan, and I am going to be discussing gallium nitride and silicon carbide and the advantages they offer in high power, high frequency RF technologies and applications. First, I will provide some general background information about gallium nitride and silicon carbide. Then I will cover some of the advantages the two have to offer in the RF and microwaves industry. Since silicon is the reigning incumbent in the semiconductor industry, I will compare and contrast its properties with those of gallium nitride and silicon carbide. I will also briefly touch on some of the drawbacks that have thus far held back the advancement of gallium nitride and silicon carbide. I'll then discuss high electron mobility transistors and monolithic microwave integrated circuits associated with the technology. I'll show some examples of commercial products currently available and touch on some of the applications that have taken advantage of this technology. And then I'll wrap up with a brief overview. Gallium nitride is a wide bandgap semiconductor with high heat capacity. It can be doped to N-type using silicon or oxygen, and it can be doped to P-type using magnesium. Gallium nitride was first grown as an epitaxial layer on sapphire via metal organic chemical vapor deposition, or MOCVD. It is more recently grown on silicon or silicon carbide despite the slight lattice mismatch. Gallium nitride has been used in solar arrays on satellites because of its low sensitivity to ionizing radiation. It has also been used to make bright LEDs covering the entire spectrum of visible light from red to ultraviolet, as well as used to make long lifetime violet laser diodes, which are used in Blu-ray players. Silicon carbide is also a wide bandgap semiconductor with high heat capacity. It can be doped to N-type using nitrogen or phosphorus, and it can be doped to P-type using aluminum, gallium, boron, or beryllium. Silicon carbide has been used in making LEDs as well as crystal detectors in early radios, car brakes, abrasive and cutting tools, and bulletproof vests. A major advantage that gallium nitride and silicon carbide share is a wide bandgap. This means high breakdown strength and higher temperatures required for the substrate doping to appear intrinsic. As a result, much higher operating temperatures can be achieved. Silicon carbide has an especially high thermal conductivity, which is a great asset in high-power electronics. The high electron mobility of these materials means higher possible frequencies of operation. Gallium nitride also possesses very high power density. Gallium nitride on silicon has 8 times the power density of the incumbent gallium arsenide technology with an increased efficiency of 70%. Gallium nitride on silicon carbide performs even better. This graphic unfortunately does not include a comparison for silicon carbide, but it provides a great visual for how well silicon measures up to gallium nitride. Silicon is represented by the inner gray lines, while gallium nitride is represented by the outer blue lines. Silicon comes somewhat close to the performance of gallium nitride when we consider maximum oscillation frequency and parasitic capacitance, but gallium nitride performs far better when we consider high power, high temperature, high current applications. Gallium nitride on silicon carbide offers superior thermal management over silicon processes. Gallium nitride on silicon carbide can withstand temperatures up to 2000 degrees Celsius. This is fantastic for high power applications. This technology has already demonstrated state-of-the-art power levels. 800 watts has been achieved at 2.9 GHz and 500 watts has been achieved at 3.5 GHz. The table here shows how drastically better suited gallium nitride and silicon carbide are for high power and high frequency applications. The 4H represents the specific structure of the silicon carbide. 4H silicon carbide is the most commonly used structure for RF applications. There are a few drawbacks that have kept gallium nitride on silicon carbide processes from gaining more popularity. Firstly, it is very expensive to grow epitaxial gallium nitride. While improvements in MOCVD equipment technology are helping to reduce the cost, it is currently still expensive enough to be an issue. In addition, silicon carbide grows 200 to 300 times slower than silicon. This is why many gallium nitride technologies settle for silicon rather than silicon carbide. High power densities also present extreme power dissipation demands on both transistor layout and semiconductor substrates. When silicon carbide can be used instead of silicon, this is no longer an issue. The high power densities can be efficiently dissipated, preventing the extreme channel temperatures that would result otherwise. Now let's talk about using gallium nitride on silicon carbide for HEMTs and MMICs. High velocity saturation means higher possible carrier velocities. These devices possess high electron mobilities. Mobilities near 2,000 centimeters squared per volt second have been achieved. High breakdown voltages mean large drain voltages, which mean high output impedance per watt of RF power. High sheet charge means large current densities, which means smaller transistors, which in turn means lower parasitic capacitances. Gallium nitride on silicon carbide transistors also achieve high cutoff frequencies, meaning high frequencies of operation. This graphic shows the cross-section of a gallium nitride on silicon carbide high electron mobility transistor. These devices are impressively reliable. They can last for more than 10 million hours of operation. This is great for highly efficient broadband amplifiers. Cree offers foundry processes in two basic families for monolithic microwave integrated circuits. 0.4 micron HEMT for drain biases from 28 to 50 volts, and 0.25 micron HEMT for drain biases from 28 to 40 volts. Cree also offers a number of discrete gallium nitride on silicon carbide HEMTs. Here's an example of one transistor they have commercially available. A few other companies also offer discrete gallium nitride on silicon carbide HEMTs. Here's an example of a lower frequency design by Triquint. Some of the more common applications for this technology include instrumentation amplifiers, software-defined radios, pulsed radars, counter IED jammers, broadband jammers, CATV modules, power amplifiers, and GPS communications. To sum it all up, recent developments in using gallium nitride on silicon carbide and high-power, high-frequency applications are a major cause for excitement in the RF and microwave industry. This technology offers high breakdown voltage, higher saturated electron velocity, and higher thermal conductivity than competing technologies. Gallium nitride HEMTs offer greater power density and greater bandwidths compared with other types of transistors. That completes my presentation on gallium nitride and silicon carbide. Thanks for watching.